you know, some humility because we weren't there. But we're looking at it and we're saying, well, you know, if he selected maneuver package A to perform that maneuver, perhaps that didn't look like it was optimal, okay? So that's all we're trying to get at. We're just trying to structure the decision and look at it in that level of detail, okay? Now, what do we do with this? Let's say that okay, this might be a cute exercise, but what do we do with this? There's two things we can do with this decision tree. We can ask ourselves, is it stable? Or is it unstable? Now, what does that do? That helps us determine if it is, in fact, a type 1 decision or a type 2 decision. Now, clearly, if you can't even begin to structure the decision, that's a type 1 decision. You agree with that, at least for the moment? You agree with that? If you can structure the decision, you don't agree? You do, okay. If you can structure the decision, all right, but it just falls apart at the least little wind blowing, it's probably a type 1 decision, okay? In this case, we say, this appears to be moderately stable. And so we have gone out on the limb a little bit and said, this is a type 2 decision, okay? You with me? And let's just assume that for the rest of the day, that we have agreed with that position, that it does appear to be moderately stable. It's not going to totally collapse when the least little thing comes about, and we can construct it, okay? And then it then fits into our type 2 decision category. Okay, now we're going to use that data. We agree with that for the moment anyway, that that's a type 2 decision. Okay. Okay, this side here, right, we're going to then take that information that we have just collected with our decision analysis study here, and we're going to give these tasks weights depending on the type of decision or whether or not there's a decision involved in the first place. So we've got this little rating scheme here that we've cooked up, and it just came off our Macintosh, our laser printer, and we cooked this thing up and we said, hey, look, guys, it looks like a non-decision ought to be given a fairly low weight in processing complexity, and a type 2 decision ought to be weighted higher, and finally a type 1 decision ought to be rated the highest because we think it's probably the hardest to process. So we come up with a rating scheme, okay? 1, 5, or 10, depending on what category this task falls into, okay? Okay, Graham said I should be over here, right? Specifically, we're dealing with, remember, 6.0 and 6.1 tasks. And how did that fall out in our analysis? Now, this is the final portion of this report that we're about to deliver to the Air Force, and our position is that, okay, Mr. Air Force, you got a type 2 decision going on here because it's moderately stable, and we have assigned that a weight of 5. Okay, are you with me on this chart? You see under processing complexity, it has a moderately high task loading rating. We assign that a weight of 6. Combine those, and in this case we just multiplied them together. 5 times 6 is 30. Our task difficulty rating on the far right-hand column is a 30. Okay, now to check ourselves and to make sure that we can prove to the customer that we understand what's going on in that portion of the mission, we've also done the same thing for all the other tasks. Okay? So we don't want to look at this thing in total isolation. We want to prove that we can do this across that dimension, and we've looked at the other tasks. And as it turns out, 6.1 is a fairly difficult task. So we're not dealing with trivia here. We're dealing with a very difficult situation, and we can quantify that difficulty. Okay? that completes this sub-portion of the task difficulty analysis. Remember, it's a combination of task loading and processing complexity. We're going to do one little other sub-module here, combine those two, and finally get with a task criticality analysis. Any questions so far on this sub-module here? Yes, sir.
Well, the weightings seem to be fairly arbitrary. I mean, do you have a historical background to draw from to pick out these numbers, like 5, 10, 6?
The weighting is on purpose. We kept it very simple for this tutorial and for the other workshops. Okay, we've kept it very simple. Yeah, good point. It probably ought to be a little bit more. For example, 1 to 10 is not a very good scale. Okay, 1 to 9 or 1 to 7, right? You agree with that? Yeah, okay. Come up with a better scale, sure, yeah. We kept it simple for understanding. I don't want to get into the details of scaling notions and statistics and all of that stuff, all right? But we can use that, all right? And we can manipulate this data all kinds of different ways. But this, you see what I'm trying to do? I'm trying to keep it simple so you can get the basic ideas going here. Okay. And if you want to add to that, then absolutely. Yeah. Okay. We're going to do one more thing here because we decided, if you remember when we started this module, we decided that we don't want to deal just with difficult tasks, but we want to deal with tasks that were difficult but also fell in an important phase of the mission. And we thought that that represented a good notion of criticality. Okay? So one more thing, real quick. We got together with a bunch of subject matter experts, and we said, okay, Mr. Subject Matter Expert from Fighter Weapons School, we want to know where are the important areas of the mission. And this is the whole air combat mission that you see listed on the left, and we have various goals identified. We've given them scaling, weights, and so forth and so on. Fairly elaborate study, but for the sake of our purposes here, let's assume that we did that. We had a group that went out to the Fighter Weapons School. We got this data from the subject matter experts. They came back and said, okay, this is how it all fell out on the right-hand side. What we're going to do then is we're going to take that weight that you see on the right-hand side and plot that on the y-axis of an XY plot. On the x-axis, we're going to plot task difficulty, which we just finished. All right? Now, that's going to give us a notion of criticality, we think, but let's see how it works out. First of all, we're going to take this XY plot and we're going to decompose it into 4 cells. We're going to say that, okay, the upper right-hand cell is highly critical. Those are highly critical tasks because they're tasks that are very, very difficult to do, and they fall in a very important phase of the mission. Okay? You kind of agree with that notion? And conversely, tasks, we may have some tasks that are critical, they're not quite as difficult, but still fall in an important phase of the mission, and so forth and so on. And down here you see we have tasks that are least critical. So we take that notion and we see what kind of plot we get. And this is the plot, basically, of the whole mission. And we're looking specifically at our guy here. And our guy is right there, all right? That's the guy we're centering on, but we're looking at the whole mission in this particular case. And we're seeing where the plots fall. Fairly interesting distribution here of criticality. Now, what can we do with this? What do you think we ought to do with it? Well, we need to understand why. Something about what, well, why did it fall? Why did these tasks fall out here? And what we can do then is we can say, well, these tasks we know are all what? Type 1 decisions from our data. We can deal with those in a certain way in design. We know also that these tasks right here are all type 2 decisions from our data. And we can begin to deal with those in a specific way. And thirdly, we can see that this group of tasks, while are difficult, they are not decision tasks. Okay? And we can deal with those in a certain way. You see how we can kind of discriminate this thing here a little bit? Yeah. Okay, you begin to see how you can play with this. I haven't figured out all the ramifications here, but that's just one notion where you can look at this thing from, okay, this is a group A, and those tasks we're going to deal with in a certain way. And you might even give those group A tasks to a certain portion of your Tiger team and say, okay, Jerry, hey, work on those. Okay, what is going on there? And Jerry's going to come back and say, hey, boss, they're all type 1 decisions. They have to be allocated to the human. All right? There is no machine known to man that can process a type 1 decision. Good stuff, right? Okay, what does it do? It goes into the human decision-aiding box. We're going to try to help the human, but there's no way we can automate that out. Type 2 decisions then go into Joe's area, and Joe is given the job of figuring out what's going on here. And Joe comes back and said, boss, type 2 decisions, or this group B, are all type 2 decisions. And they're candidates for AI. Okay, good. All right. C are critical tasks, but they don't require any decision processing. Okay? So we're going to treat those with just normal software and hardware treatments. Okay? Now you may come back and say, or you may go back to your boss and say, boss, we got a bunch of type 2 decisions here, but we're not really all that good in AI, so let's bring in some AI experts, or let's get smart in AI. Okay? So you see where I'm leading here? You see the kind of the notions I'm trying to get at? Okay? Good design drivers we're starting to get to. This is the first major design driver. If you had to look at this package today, we're going to be looking at a number of design drivers. We think this is one of the major ones that is going to help you to drive a design in the direction that you think is going to achieve mission success. Okay? That essentially completes the critical task analysis or criticality analysis module.
Okay, what sort of information requirements do we have? Well, we need to know all the physical parameters of the situation, need to know how they relate, what our status is, as much about the other person as we can determine. The information requirements analysis, we're kind of laid out here in template format using the IDEF notation. What we're going to do is use the results of our task characteristics and our critical factors as some sort of control mechanism on the task that we've defined. Take a look at the underlying process and mechanism models. We'll spend a little more time with them in the next module of the tutorial to generate our information requirements list. That and the processing models then flow into the system concept definition, where we analyze the validity and the utility of the results that we've generated. The information processing mechanisms themselves can be thought of as taking a look at how we actually handle information within the environment that we work with. In this chart, we have a nice dividing line between, on the one side, all of the silicon-based computing intelligence in the system and all of the carbon-based computing intelligence in the system there. We realize that we need to be able to put that together and to determine what the mechanism is to generate the output required to stably control the system and achieve maximum mission success. We do that by recognizing that the strategies that we're going to take a look at from a conceptual design viewpoint can be best expressed in terms of the ones that are familiar to us every day as human beings, realizing that they do have computer components and counterparts also. So we have three major categories that we're going to take a look at here. And we've got a set of definitions of each one of the major classification elements that we can refer back to within what we're doing. The major ones to focus on here are within the knowledge structure itself, to realize that we have a fundamental difference between doing mere fact recall and data retrieval and the application of concepts and principles, which is fundamentally a very high-order processing mechanism. The decision processing mechanisms we've already covered in terms of the complexity and the way we type them, and so we're able to discriminate between the processing required for them. The information management itself runs through the entire gamut of being able to acquire, manage, control, correlate, project into the future, make some inferences on what's likely to happen, and determine what sort of assessment is necessary to complete the picture. What we've done with this slide here is to take a look at our mission-oriented task and just go through in a very common sense approach, guided by some of our subject matter experts, to determine where major chunks of knowledge processing, decision processing, and information management occur. This first cut gets moderated several times and is reviewed at many different levels to complete the picture. The completed picture that we're going to work with, having been through a couple of iterations, is best expressed by this view graph, where we have the three major tasks that were recognized within the mission decomposition that Kevin produced as having multiple interrelated tasks in a compressed time environment, and all of them having high criticality to mission success. And those are the maneuver to intercept targets, determine the weapon firing sequence, and maneuver to launch position. And in fact, this problem set that we are working based upon the video that we saw is the very first part of this maneuver to intercept target, which is determine the optimum tactical maneuver. We're going to further decompose that as we get into the model that we're going to use to assess the value and the worth of the conceptual design that we're proposing. Now, we try to gather as much information together as we can, put it into a format that's readable and usable by a wide number of people for a lot of different purposes within the data gathering, data processing, and report generation format. So we put together several different sorts of worksheets here, and you've probably seen some of them. They're aids to collecting data and to presenting it. Hopefully, it helps to focus the critical evaluation that the many team members on our Tiger team are able to bring to resolving the problem. Okay, within this one here, I'm sorry, over on this side. Within this one, we have the tactical objective is to maneuver to intercept target. Our task is to determine the optimum tactical maneuver. We fill in the first part of that based upon what we've already done. We've captured off what the information processing mechanisms are. In this case, there's no knowledge structure to speak of that needs to be handled. We have a recognized type 2 decision processing mechanism, and we have no very heavy information processing, information management mechanisms there. We're able to write up the characteristic statement here that presents it in a nutshell for anybody, and then determine what sort of information requirements we've got. We realize that we need to be able to assess the intercept geometry. That's primary. We need to be aware of the EW situation in regards to both our own capability and the other target. We need to also have an idea of what the target raid is like. Is it only a one-on-one encounter, or are there more hidden within there? Lastly, we need to be able to analyze that several different ways and be able to provide an assessment of what these results are. As we tear down within the subtask structure, we find this one is analyze the intercept geometry, perhaps the most important component of what we had over there. We recognize that this actually does have the necessity to do some fact recall and to apply some concepts within it. We're going to take a look at what they are in the next module. There's not a lot of decision processing involved, but we do have the requirement to acquire and to correlate some of the information that we managed to obtain. We write out the characteristic statement and realize that we have the information requirements from that. And these information requirements are basically to correlate the target aspect angle with the optimum target aspect angle to guarantee the highest level of probability for mission success. We need to correlate what is referred to in fighter weapons school as antenna train angle. That sounds like we've committed to a technology, doesn't it? Antenna train angle. That would be radar. Well, in fact, that's really just the statement within the training curriculum that's the difference between what your velocity vector is and what your instantaneous line of sight to the target is. It does have a radar component to it, but we're trying to keep this separate from the technology that could be brought to bear. Lastly, we do need to know what the range of the aircraft are during the situation itself. This is, of course, one of the fundamental physical parameters and is used to gauge any number of things within it. We tried to keep the number of information points to a minimum so that we can express it simply in a model, analyze it simply in a model, and build the added complexity after we've decided that it's really worth doing. So here we've listed out for our 3 mission objectives and the most important of the task, the information requirements themselves. And this entire thing flows throughout the package. We realize that, in fact, there are some other things that need to be brought to bear when you concentrate on different aspects of implementing the mission plan itself. And these things feed back and forth. It becomes a very complex, dense situation. We're going to focus on the one thing, analyzing the intercept geometry for its contribution to situation understanding, because this seems to be the crucial part, the heart of the problem that we've come to within our video this morning. So we understand that within the knowledge structure itself, we've got a concept application to be made. Over in information management, we have to both acquire and correlate that information. This just lays out the fact that we recognize what our processing components are. We've got some idea of the strategies that we have there, and we realize that what we need to do is to develop some sort of logic to determine optimum intercept geometry, to be able to assess that. This is probably the key point of what we need to do both tactically and within our design criteria itself. If we can't assess the validity of that optimum intercept geometry in a simple model, it would likely prove difficult to mechanize in any sort of realistic fashion in a tactical environment. Okay, we're having finished up the information processing. Are there any questions about what we're really trying to do to resolve the problem that we've been handed as a Tiger team? Okay, we're going to jump into the concept definition of the system. Remember, this is, in Fred Brooks's words, trying to take a look at conceptual design issues that allow us to define the system and make some design issues known early enough in the game that we can, in fact, do something about them. This gives a real quick overview of some of the distinctions between the concepts and the functions. We have a couple of aircraft concepts up there, and it's fairly easy to take a look and notice the distinguishing features, some of which are noted, some of which aren't. For instance, the biplane, an older design, does have retractable landing gear, whereas the monoplane, a newer design, doesn't. In fact, to be able to evaluate which concept is best, we need to understand what the domain is that we're working in there. In this case, our domain is pylon racing. So we have a mixture of both straight line performance and turning performance that needs to be blended together to achieve a winning racer within the pylon. Knowing what that function really is, we're then able to apply all the aerospace and physics formulas to determine what the relative advantage of the monoplane with cleaner drag and higher speed on the straightaways is relative to the biplane with a better turning radius, more lift, however higher drag on the straightaways. Without bothering to actually make the decision here, because we're not going to go pylon racing today, we move on and take a look at how we're going to analyze the concepts for the optimum intercept geometry. We recognize that we have at least one concept definition there. We're only going to choose one to grind through the crank today. In fact, we might have several different concepts, one behind another, that we need to evaluate in the real world. We decompose them into functions, run through a process model to understand what needs to occur within that, just like in the manufacturing realm. We have a system process description, and we have a set of algorithms that we're going to evaluate within that. Now, the algorithm that we're going to use to do our system concept definition analysis is listed out here. The functional component that we're taking a look at is the intercept geometry, maneuver to target, the components required to generate an optimum intercept geometry logic and to enable us to verify how good that is. We need to identify what kind of processing is involved, what the information needs are. We need to be able to structure this candidate algorithm, and we'll spend a little bit of time taking a look at that in a simple physical model later. And then we need to determine both, can we specify the processing model in sufficient detail, and is it feasible enough, and does it have the desired utility to actually make the prototype and the system work as we require. Okay, we have a system concept for the entire cockpit, aircraft, man, machine, and weapon system within modern fighter combat systems. We're going to focus on the situation assessment processor here. We're going to narrow down into the maneuver to intercept target, into the subtask, determine the optimum intercept geometry. We define a couple of things. Let's see, we need to actually put that one up. We also need to understand what the process analysis is like before we get into it. Recall, we've got here some sort of start and ending conditions there. We know from our previous analysis, in fact, that we're going to need to do some information acquisition and correlation, and we're going to need